All right, so this video is on the chain rule, which is the last rule to go in our derivative chart. And it quite literally is the last rule of how to do derivatives. It's probably the most, I guess, I mean, I don't know, it probably depends on the person, I suppose, but I think it's probably the trickiest of all the rules, mostly just because the setup isn't automatic. There's a little bit of work to get it in the right form, I guess, or to recognize the correct form, and then from there it's not too bad, but that's definitely a challenge. So anyway, we will take our time and make sure that we've got a good understanding of the setup piece before we even do the derivative. So that's what I'm going to do first. So that'll fill in. Here's our chart. I actually just rewrote the chart and kind of scrunched it to the left a little bit from the last time, so I swear I didn't add anything. This is where we left off at the end of the quotient rule video, but this way I have space to write in the last rule. So here's our chart, and again, just for the one last time, I'll remind you that on the left, what you see are the sort of shortcuts, the derivative building block derivatives, you might say. These are the basic, I think, 11 functions and 11 types of functions that you might want to have the derivative of in some form or another. And if you just have one of those 11 on the left, in the left column here, you would then say, oh, well, what's the derivative? Oh, okay, it's right here in the right column. So what's the derivative of sine of x? You say, oh, okay, it's cosine of x. And this is very handy for obvious reasons, in that it is a nice way of not having to really do, well, any work to compute a derivative. And these guys on the right here in the right column represent someone, you know, going through the awful, terrible definition of a derivative formula and computing and simplifying and doing some crazy stuff. So we're grateful to them that we have that. On the right, and by that I mean under the rules over here on the right, these are our rules so far. And we've got 4 rules that we've done in the last few videos. We've got rules to help us handle what do we do if we have one of these guys here on the left, one of these probably building block functions, but modified. So what do we do if there's a number in front of a function that we know about? That's the first rule, the coefficients rule. And if you remember, it just said just do the coefficient, carry that over, and just do the derivative of the stuff with x's in it. And then we thought about, okay, well, what else could we do, or what else could we have? Well, maybe we've got more than one of these building block functions. Maybe we have f and g, where, you know, these are just 2 functions, whatever they might be. How do I deal with adding them, subtracting them, multiplying them, or dividing them? And that's what the next 3 rules tell us. To add or subtract, you just sort of do what you think you can. But for multiplying and for dividing, we needed the product rule and the quotient rule. And these were a little bit more involved, I guess, in terms of there being a little more to do. And so, you know, we took our time, though, and as much as they are sort of messier and certainly longer, it's not really harder, I don't think. There's just more, I guess. It's longer. It's going to take you 5 minutes to do a question about sine of x divided by x squared plus 1. Whereas, you know, if it was just sine of x, you'd know the answer. If it was just x squared plus 1, you'd know the answer. So it's just a little bit more time, but not really too much trickier, I don't think. Okay, and at the end of the day, no matter what, no matter which situation we're in, we may need more than one of these rules. We did the last example, I think we did, involved a problem that was a fraction, and so it needed the quotient rule. But one of the components, I don't remember whether it was the top or the bottom of the fraction, was also a product. So therefore, I kind of needed the product rule and the quotient rule. And you know, we worked through that, and that was all right. So, and this is really it. I really do mean that this is sort of, I don't know personally much more of how to do derivatives aside from what you see in front of you here, plus the 5th rule, which we're going to do today. But that's about it. So this is the derivative story, final chapter. So, all right, so we're going to do this last rule, which I'll say is called the chain rule, which is not a very mathematical name, I guess, right? Product rule, quotient rule, addition, subtraction, these are all math words, and you know what they mean. Chain's not really a math word, and it isn't, but, well, I'll tell you the not very funny at all story about why it's called the chain rule after we do it. So, all right, so we'll come back and fill that in. So what is the chain rule to help, what is the chain rule going to help us do, or this last rule? Well, what are some other sort of adjustments or modifications on famous functions might we have? You know, so we've talked about how if I have, you know, sine of x and x squared, for example, I could add them. Well, we have a rule for that. Or I could subtract them. Well, we have a rule for that. I could multiply them. We have a rule for that. Or I could divide them, and we have a rule for that, right? So we've sort of done the four basic, what you learn in first grade or second grade, math operations, I guess, on two functions. So I've sort of done them all, which means there shouldn't be anything more, I guess, left to do. And there isn't, except there is one more thing that you can do with two functions, you know, or one more sort of natural or basic thing that you might need to do to two functions. And for which we might want to have a rule that would help us then answer the question, which is to say, if, let me space these out just for a second here. If f of x is sine of x, and g of x is x squared, so what I just wrote down, let me give them labels. Let me call sine of x f of x, and let me call g of x, or let me call x squared g of x. Okay, so again, I could do add, subtract, multiply, divide, but what else could I do with two functions? Well, one of the other main things that you learn, I think, in, I don't know, algebra class or maybe a pre-calc, I guess, is what I think your teacher would have called the composition of two functions. And by that I just mean, what do I get? Whoop. Okay, that looks like a W, right? Yeah, ooh, no it doesn't. What is f of g of x, and what is g of f of x? So, and you may have, your teacher may have written it kind of like, how do they do this? F-O-G, like, looks like fog. I don't know. I think some people write it that way. I don't care for that, but that maybe is what a teacher wrote at some point for you. I really find that kind of dumb, so I'm going to immediately erase that. This to me makes a little more sense. What does this mean, first of all, I guess, right? So this just is saying here, if we look at part A, what is this, right? In other words, I'm going to ask you before we start to go do crazy stuff in calculus, just take a step back. What does this even mean, I guess, right? So this is saying, if you do f of g of x, then what this basically saying is saying, all right, you've got g of x, that's a thing. In fact, it's x squared for this problem. And I'm going to take that and plug it into the f of x function. But rather than just putting an x right there, I'm actually going to put, in this example anyway, I'm going to put g in for x. Which means basically what I'm saying is, if you want to do this sort of slow, you could say, all right, well, that's not really f of x then, is it? It's f of g of x. Well, g of x for our problem is x squared. So really, it's actually just f of x squared. And again, it sort of helps if you say it fast like that, f of x squared. Because then it might help you think, oh, what's f of x squared? Well, if I put an x squared there, then that means I should put an x squared there, which means this is really just this, sine of x squared, rather than just sine of x. Okay, so far this isn't anything super fancy, right? But just to have a recognition or an acknowledgement of what does this even mean. And this is called the composition of functions. This f of g of x or g of f of x in math is just called composition. It's not important. But actually, if this rule, I already told you this rule is called the chain rule, it actually should be called the composition rule, because this is the type of function, or this is the type of modification that it's going to tell us the answer for how do I do the derivative of something that looks like this. So Anyway, and just to emphasize what's the difference, right? So if I swap them and say, okay, now how about g of f of x? Well, you don't have to like get too bent out of shape about this. Just sort of do what we just did, but, well, you know, do it in steps here, right? So you say, all right, what's that? Well, in math, you guys know, you always start on the inside of parentheses, you know, when you're doing computations and arithmetic, you always look if there's parentheses, that's what you do first. So the same thing is true here. So I see g of f of x. So first I should assess, well, what's f of x? Oh, f of x is sine of x. So let me plug that in first. Okay, and now it's saying, well, what is this? Okay, that's g, that's a function. G of x is a function. But I'm not actually putting x, I'm not plugging x in there, am I? I'm plugging sine of x in, which means I say, oh, okay, that means in my g of x function, which is up here, I'm putting sine in for x, which means I should put sine in for x. So if let me erase this arrow here, it's in my way. So this is really sine of x squared. Because again, it's the g function. Basically, the way to think about it is g. What is g? G is the squaring function, is kind of a way of thinking about it, right? That's if you wanted to give it a nickname, you'd say, oh, it's the square function. It squares things. If you plug 2 in, it gives you 4 as an answer because that's 2 squared. So if I plug sine in, it should give me sine squared. Sine squared. Okay? So, all right. Again, this isn't rocket science, I hope. Before I move on, though, let me say, just, I don't know, a word of, I guess, caution or just a notice to the following. These are different, right? I hope that everybody's in agreement that these are two different things. I realize that they are kind of made up of the same things. You've got a sine and an x and a square. But these are very, very, very different things, okay? The one on top, if I wanted to say what is the one on top there, that's saying do x squared and then plug that into sine. The one on the bottom is saying do sine of x and then square the result. Okay, so in fact I would get different things if I put different values into this x values in. You'd get different answers whether I put it here or here. You get a different answer if you plugged in x equals pi over 2 or something like that, or whatever angle you want to plug in. Okay, so these are definitely different. So, but in any case, these are two very good examples of compositions of functions. Okay, so hopefully that's at least a reminder of what those are, because the moral of this story and what is this whole lesson about is that if you see something that looks like this, again, what have we been doing for the last week with these lectures is how do I do a derivative, right? That's always going to be our question. How do I do the derivative of maybe something that looks like that? And the answer is going to be, well, if you can split it up and write it like a composition of two functions, where you say here's f and here's the g, then you're going to be able to do the derivative using a rule. Just like in the last couple of videos for the product rule and the quotient rule, we had to say, okay, someone's playing the role of f and someone's playing the role of g, and if I name those two things, then on the right here was how do I do the derivatives, right? Oh, okay, there's a nice formula, I guess, right, for how you do the derivative, as long as you can identify f and g and the derivative of f and the derivative of g. Well, the same is going to be true for this new rule that we're doing, this chain rule. It's just that it's going to describe how do I deal with something that looks like this. And the answer is going to be, well, if you can tell me the f and the g and then the derivative of each guy, which that won't be hard, we could then maybe construct the derivative of this. Okay, maybe just based on knowing what the derivative of sine and the derivative of x squared are, because those are both easy. All right. So I'm not even going to tell you the rule yet, though, because I want to do a couple more examples of this composition business. So now I've taken baby steps into the pool here by giving you this problem or this line of questioning first, which was to say, if you have an f and a g, that's how I started this slide. I said, if you know what f and g are, and I just made up some things for f and for g, could you tell me what f of g of x is, or maybe swap them and tell me the other one. Well, that's not going to be the order in which we see problems. When we see problems, it's not going to already say, oh, here's f and here's g, do the composition, and then tell me what you get. Okay? We're going to have to be able to do this in reverse. So in other words, we're going to be asked a question like, what's the derivative of this? And we're going to have to be able to backtrack and say, oh, that guy, sine of x squared, I need to recognize that as the sine function with x squared plugged into it. Now, you should immediately be, concerned if you're not immediately a little bit worried about, well, how the hell do I know that, right? And that's very reasonable to feel that way right now. And if you didn't, I would fear that you're not actually understanding what it is I'm going to be asking you to do, because what I'm going to ask you to do is not easy or not trivial anyway. So, but the perspective is that I'm going to say either, something like this problem, sine of x squared, or maybe this one, and I'm going to say, tell me the derivative. Well, in order to know the derivative, we're going to have to be able to work backwards and say, okay, if you want to know the derivative of this, I'm going to first have to identify these two pieces. Okay, and then I'm going to invoke this rule that I've not given you yet, but I will, which will then tell us what the derivative is. All right, so I want to give us a little bit more practice first on going backwards now, right? So instead of me giving you f and g and you telling me this, let's say if I tell you this, could you unravel and pick the right f and g? Okay, so let me go to the next slide and give us a clear space here. So here's the question. Identify the f of x and g of x so that each of these looks like f with g plugged in. Okay, so we're going to do several examples of this because this is hard. And I'm going to give you some strategies for how to do this, but let's try one or two, just sort of as is, and then I'll give you some tips for how to maybe do this to spot these a little bit more easily. Okay, so let's try just hopefully not a bad one first. So what if I have e to the x squared? Okay, so I guess, big picture here, right? If I'm asking you what's the derivative of this, you don't know what the derivative of this is. And in fact, I don't think you really have any great way of knowing this. It's not in the chart. E to the x is in the chart, but e to the x squared is not. And it's not a product. It's not e to the x times x or something like that. Like, it's not one thing times another thing. So it's not the product rule, and it certainly isn't the quotient rule because I'm not dividing here. So this is a problem where if I asked you what is the derivative of this, you don't know the answer right now. And we're not going to know the answer for a little bit still. But I think, if you believe me anyway, if we can rewrite this as a composition of two functions, f and g, we're going to be able to write the derivative. We're going to be able to answer the question, our ultimate goal, which is to be able to say what's the derivative of this guy. But before we even do that, can I at least do sort of what is step one, which is can I rewrite this as the composition of two functions, namely that. Okay, so I'm gonna do just like we did for the product rule and the quotient rule. I'm gonna sort of try to get my thoughts organized, where I'm gonna say, maybe I'll come over here on the right, and I'll say, all right, so this thing right here, that should be, maybe I'll do it underneath. So I'm looking to say, who's f and who's g? Okay, and again, the key thing here is that I'm trying to make e to the x squared look like this. I'm trying to make it look like one function, g, which is being plugged into another function, f. Now when I look at e to the x squared, my guy right here, I'm hoping that at least the candidates for what these two things might be are a little bit at least jumping out at you. That it certainly looks like I've got an x squared in my problem, and I've also got an e in my problem. In fact, that's literally, those are the three things that are there. I have an e and I have an x squared. So the question you should be asking yourself is, if I want to make this look like one function plugged into another guy, you might start by asking yourself, okay, well, this should be, and these should all be more or less kind of famous functions, or at least for easy ones. So I'm trying to say, all right, well, so let's see, what do I have? Well, what is the first thing I'm doing as I'm doing x squared, right? If I was actually ask you to evaluate this, and I want to say, tell me what do you get when you plug in x equals 2? I would hope that on your calculator, you would say, if I said, tell me what you get when you plug in x equals 2, I'm hoping you would do 2, and then you'd square it and get 4, and then you would do e to the 4th power, and you'd get whatever that is. So my first tip for how do I pick how to pick f and g for the quotient for the chain rule. That's what we're doing. So my first tip is g of x is the first thing you do if, let's say, you are plugging in an x value. Okay, so I'm going to try to give you, I think, 2 or 3 tips over here on the right that should generally work, or should generally at least be helpful. So tip number 1, if I'm trying to think about what's f and what's g, I mean, again, hopefully you sort of at least know that f and g in this problem are probably e to the x and x squared. But the question might be, well, which is which, right? Or maybe you don't even, maybe you're not seeing that at all yet. I don't know. But a tip for you is to say, well, if I'm going to try to make my guy look like this, look like f with g plugged in, well, the first thing I would do, just like we did on the last slide, right? How did I figure out this? Sorry, I'm going to keep erasing and redrawing probably the same comments here, right? But how did I figure out what this was? Well, I first said, well, let me do the g first, right? That's what I did. I said, oh, okay, what's g of x? Why? Because that's on the inside. G of x is on the inside. So I said, all right, first let me plug in g of x right there. And then the second thing I did was I then said, okay, now let me take that and plug it in for x, and that's how I got sine of x squared. So the order in which you would do things is first you do g, then you do f, okay? So coming now from our perspective, my first tip for you is to remind you that g is the first thing you would do if you were plugging in an x value, okay? And then I should maybe put a second sentence here, maybe I'll put a semicolon here, and I'll say f is everything else. Okay, or f is the rest of the stuff, basically. Okay, so even just using that tip alone, I hope, right, that I've convinced you that if you were to actually try to plug a number in here for x, you would first do x squared. So hopefully, even if I'm just kind of following this first hint over here, I hope I would maybe come to the conclusion that g should be x squared, because that would be the first thing I would do if I was plugging in x value, and I would square it, right? Okay, and then what else am I doing? Well, so that's basically saying, okay, so g of x, I'm just going to cross this out for a second and say, so I'm saying g of x is really x squared. So, all right, fine. So now this guy needs to be thought of then as f with x squared plugged into it. So, okay, well, x squared, okay, what function am I plugging x squared into in order to get this? And hopefully now the answer is obvious. Well, I'm plugging it into the e to the x function, right? I'm literally taking g and plugging it into x in the e to the x function. And indeed, if I tell that story one more time, I think you can sort of confirm, do I have what I wanted? Erase this. So my goal was to make it look like that, to make it look like f with g plugged in. So let's see, so g is x squared, okay, and then if I put x squared into the f function, in other words, right, I put x squared there, then that means I would put it there, which means I would get that. Okay, so I think, no matter how you kind of come to it, or hopefully this makes sense, that this is the correct setup. This is the correct f and g that actually make my original guy look like that. I know I haven't told you why we need to make it look like this yet, but I promise I will soon. All right, but even just as an exercise, can we pick the right f and g? I hope so, right? And this is the first tip that I have for trying to, if you're confused, I mean, some of you will be very good at this and you're just going to spot it and you don't need any tips, and that's great. And if you don't, then you're good to go. But if you're kind of like, I have no idea what this is, try to maybe use this tip, and I'll write down one more tip in the next example here. But I would say, regardless of how you get there, when you sort of say, okay, I think I got it, you should always check, is this right? And the way to check it is just to ask yourself, if you take whatever you wrote down for G and you plug that in to the X's that you wrote down for F, do you get this thing that you started with? And in this case, I do. So I think I'm good. Now, if I had gotten them backwards, so you don't necessarily have to write this down, but let me just play a little pretend here. Let's say I kind of knew the right pieces, but put them backwards. Well, then when I check, I should be able to say to myself, is this right? And again, the way to check it is to say, if you plug G into your F, do you get the thing that you started with? Well, I would ask myself that now if I'd say, all right, so I'm going to take G and plug it in for X, and is that the same? So if I did that, I would get e to the X, and then that whole thing squared, right? I would get, if I was checking, I would say, okay, so it's e to the X, and then I plugged it into the squaring function, which means I would square it. Okay? Now, maybe you have to think about it for a second, but is that the same thing as what I started with? And the answer is no, it isn't. In fact, this is e to the 2x. If you'd prefer, you could say that. But it's not e to the x squared. It's e to the x and then squared. I know that sounds like I just said the same thing twice, but it isn't. It's different. This would say do e to the x, then take the result of that and hit the square key on your calculator. Whereas this would say square x first and then do e to your answer. Okay, and it's different. You'll get completely different answers depending on the way you do it. All right. So that's one way of just and you absolutely, I mean, unless you're really, really good at this already or get very good at it very quickly, you should always check. Did I set this up right? Because again, unfortunately, if you set it up wrong and then proceed to do the whole problem that way, it's obviously not going to be right. Okay, so one more example, and that'll sort of give rise to my second tip over here. So one more example here. Maybe I have something like cosine of x cubed. Okay, so again, my question is the same to you. How do I express this as the composition of f and g? So in other words, how do I express this cosine of x cubed? How do I write that as one function plugged into another function, namely the g function plugged into whatever f does? Okay. So I could, if I like my tip over here on the right, g of x should always be the thing you do first. Now again, if I asked you to tell me, what do you get when you plug in x equals 0? I hope on your calculator you would say, if I'm supposed to plug in x equals 0, I hope the first thing you would do is you would say cosine of 0, enter, and you'd get whatever that is. It's 1. And then you would hit the cube key second, and you'd say, okay, whatever I got for that, now I'm going to cube it, and that's it. So my tip over here is still pretty good, right? That it says whatever you do first, try that for G. But I'll throw in a second tip here, which is to say also, actually, you know, if you actually just look at our setup here, you can kind of almost see, if you squint at this, don't you kind of see, like, you see parentheses here that are kind of saying, do this first, namely G, right? Do G first and then do F. That's kind of what that says. Well, you actually see parentheses here, don't you? Now, of course, not all problems have parentheses, but a lot of them do. And so you can actually sort of use as a second tip for picking G. I'd say G of X is, I guess I should say usually, the function or the expression, I'll say function, that's inside the parentheses, if there are some. I mean, you might not have some, but parentheses, I think that's spelled right. So another place to look and say, well, what's G and what's F? G is often, if there are parentheses, G is generally what's inside the parentheses. Because again, in math, you know that you do the things that's in parentheses, that's what you do first. So it's really just sort of another way of saying the first rule here, right? G is usually the function that's in the parentheses, and then again, I would say, and then F is everything else, or F of X is everything else. And by everything else, I just mean, what do you do after you do G? Okay, so in any case, however you slice it, hopefully, when I look at this problem, I'm saying, okay, so what is it that I'm doing here? Well, you're doing cosine of X, and then you're cubing it. So the first thing I would do, or the thing that's in the parentheses, is cosine. And then what am I doing to cosine? I'm cubing it. So in other words, I'm plugging it into the x cubed function. Okay, so I should just double check myself now, right? Did I get this right? So I should ask myself, is it true that what I've written down here, when I do this, do I get what I started with? So let's see. So this would be saying it's F with G plugged in. So G is cosine. So is it true that if I put cosine there, do I get this? And again, hopefully you can pretty immediately confirm that yes, you do, right? When you put G in for X in F, you get cosine of X cubed. Okay? So, so that's, again, I don't know, I mean, I could do 5 more examples, and until you sort of try them yourselves, I guess you probably don't know for sure if you get this or not. So, but you'll have lots of practice with these to try to make sure you get them set up correctly. Again, these 2 rules are pretty good for helping you to maybe pick what's what or who's who. Maybe I'll just, since I have space here at the bottom, I can cram one more in maybe. Maybe I might have something like, I don't know, the square root of ln 2 ln x or something like that, plus 5. Okay, so again, I'm trying to say this is somebody plugged into somebody. Oops. Oops. Okay, so I'm trying to identify there's a function that's then plugged into another function. And again, my tips over here are helpful. G, usually when I pick G first. So G is the thing you're going to do first. So again, it's what's on the inside. You could also think about G is the inside function and F is the outside function. Okay? So if I plug in, if I was to plug a number in here, right, the first thing I would do is that stuff. And then the last thing I would do is I would hit the square root key at the end. So the first thing I do is I would do 2 ln of x plus 5. So that should be G. Now I know there's a couple of things there, right? There's ln and there's 2 and there's 5. So why did I grab all of that, I guess, is a reasonable question. Well, remind yourselves, right? I gave you a tip, and I'll give it to you again later when we do more complicated examples with chain rule. You know, when you pick a rule and when you say, I'm going to start doing a rule, you do have to pick a rule that uses everything in your problem. So if I just said ln of x is g, then I say, okay, so what am I plugging g into? Well, I've kind of neglected the 2 and the 5 if I just take ln of x. So I can grab all of that stuff. Why? Because it's true, right? All of that stuff, 2 ln of x plus 5, that whole expression, that's what's being plugged into what we hopefully recognize as just the e to the the square root function. Right? So again, if I'm trying to say this guy that I just wrote down and started with, he's one function plugged into another function. Well, who's who? Well, this looks like, I hope, that guy plugged into x in the square root of x function. And indeed, that's correct. All right? So you sort of have to just do these and try them. And again, if you get it wrong, it's probably because you either swap them, so just swap them, you know, like if you had these backwards, just swap them, or because you've left something out. So never leave anything out. When you write down the chain rule, you should use everything that you see there, should be somewhere, so that at the end of the day you can say, oh, the whole thing that I was started with looks like this, looks like f with g plugged in. Don't leave things out when you're doing this. Okay, so far obviously I haven't mentioned the D word, the derivative word, in like the past half hour. So let me correct that and do that. So why is it that I've wasted the last 15 or 20 minutes doing these types of problems? Because these are the types of questions that we might want to know now. Well, what's the derivative of somebody like that? Well, I don't know the answer, right? I've done this cute little thing here where I've done this rewriting it as a composition of f and g. But that doesn't tell me what the answer that doesn't tell me anything about what the derivative is. I need help, right? So it's, oh, right, well, this is sort of the last way, though, that I might combine functions together, right? I could add them, I could subtract them, I could multiply them, I could divide them, or I could, and again this is called, I could compose them. I could send one of them into the other guy. So you say, all right, well, if you did that, is there a way of getting the derivative in a not so painful way? So if I want to know what's the derivative of that, cosine of x cubed, well, I know the derivative of x cubed, and I know the derivative of cosine, don't we? Those are both in our chart. So maybe I could actually get the derivative of this thing just by knowing the derivatives of these guys. And obviously I'm setting you up here, right? That would be if the answer was no, then I have exactly wasted 38 minutes of your life. But no, the answer is yes. You can do the derivative of a complicated composition of functions like that if you just know, if you can do this, what we just did, namely identify what f and g are correctly. And then if you know what the derivative of f and the derivative of g are, you can assemble the derivative of the whole thing. Okay, so let me give you the punchline finally then of what is the so-called chain rule. And this is our last rule, 5. So if we have the composition of two functions, we can get the derivative by doing the following. So if we have a composition, right, f with g plugged in, okay, then the derivative you can get by doing the following. You would do the derivative of f with g plugged in times the derivative of g. Okay, so the chain rule, that's it. Okay, so this is the chain rule. This is our last rule. And it tells you, how do I do the derivative of something that looks like this? Okay? And again, that's exactly what these last several examples have been, right? Why did I make us do this? Because these guys here were three examples of a composition of two functions, right? This first guy was an example of a composition of e to the x and x squared. And the second guy was cosine with x cubed. And the third guy was the square root function with this 2 ln x plus 5. So why did I make us do this? Well, because that's exactly the setup for the chain rule, this last rule. So if you have something that looks like one of those guys, like we've just spent the last half hour on, then here's how you would do the derivative. And let's dissect this for just a moment. First of all, good news about the answer. It only involves what? It involves g of x. Well, we're going to probably already know that, because that was right there. It's going to involve g prime. Well, if you know g, you can probably figure out the derivative of g. And it's going to involve f prime. Well, and again, if we know what f is, we can probably figure out the derivative of f. So just like the product rule and the quotient rule, there's very good news, which is that in order to know the derivative with the chain rule, all you need to know is if I can identify f and g and write down the derivative. So I'm going to do what I just did, what I've always done, which is to sort of say, tell me f and tell me g. Okay, and then I'm going to probably use the chart or some other rule to tell me what's the derivative of each guy. Right? Okay, so do the derivatives. And that means I'll know these four things. And these are actually all I need to know in order to write down my answer. Because look, my answer actually, I only actually need three of them. Those things. And you've got them. Here, here, and here. Okay? So you're going to be able to assemble the answer to the question pretty easily, assuming you can do sort of all of the setup. And that's where, you know, that's where the devil is in those details, because that's not going to always be the most trivial thing to do. Okay, so the reason why this is the hardest rule is because this part, just getting that, is work, right? Identifying, oh, that's the correct f and the correct g to make the guy, to make the question look like this. Okay, well that's some work in order just to get us set up. Okay, now once I get us set up correctly, then I do my usual find the derivative, okay, I got that, and then here's how I assemble my answer. Now I'm just going to say, be careful when you assemble the answer, and we'll do many examples of this, but you have to be just ever so careful when you assemble the answer. This is not f prime times g. This is f prime with g plugged in to it. Okay? So when I do my four pieces down here, whatever I get for g, whatever's here, I'm going to plug that in to x over here, wherever that might be, wherever my x's are. I'm going to plug that in. That's what this first piece is. And then just times g of x, whatever's down there. All right? So there's many, this sounds awful, but there are many places you can go wrong here, I suppose, which again is why this is hard, the hardest rule. But we're going to do many examples together, and hopefully I'll snuff out most of the errors and anticipate most of them that you might have. But ultimately, at the end of the day, you need to try a bunch of these and, you know, do 5 or 6 of them, and if you get them all right, then you're probably good. Then you, I think, then you get it. If you're finding yourself really kind of stuck and not getting these, then you know, come back and sort of look at this again and maybe try to rewatch some of these examples. And of course, as always, please, you know, send me an email if you have questions. So, all right. So I'm going to stop this video because obviously I haven't done any examples of this yet. So I'm going to stop this video just to break it up so that it's not too long. But immediately you should watch the next video, which will be examples of using this chain rule, this so-called chain rule that we have here, in order to do some practice with these on real problems.